So, we're talking about graphical analysis of motion. Um, you'll see when you get the study guide. So the study guide that's coming out this week, roughly a week before the test, those are closer examples to what's on the test than the homework. The homework is kind of warm up, has references to other science stuff. The test review is not required for you to do, though. If you're just extremely confident you can do it all. You don't have to turn in that test review. It's due 48 hours or so before the test, or we'll go over it 48 hours or more before the test. Okay? So it's not for a grade, but it doesn't help you if you wait on it forever. So the goal is actually you should be finishing up the homework kind of today and tomorrow, Wednesday, Thursday. It's due at the start of class Friday, but that should not be like I'm squeaking in to get the last problem or two done, like in the hallway before class. Nah, that's not the intention. Okay, and then after tomorrow, there's not immediately another assignment I'm going to grade, but there's test review problems out. So you should be working on those and asking questions. All right, graphs. On the test and on many future tests, I will ask questions about graphs. And they're actually really simple, but you have to realize what the graphs can and can't answer. Okay, so by now you know the equations for stuff. If I have a graph of what's plain old x, no, it's not. Sorry, we won't call you out. It's actually position. So I'm tracking the position of some sort of object through time. I'll see if I can figure out how to play this little game for Friday. Might have to just clean a lot of equipment. But it's pretty fun for about 15 minutes. So what is this thing doing here at 10 meters for the first 1 second? It's just sitting still. It holds the same position. Oh, okay. So it's pretty obvious. And then it's gaining position over time. If I change my position, if I change my position over the course of time, what's that one? Okay, it's the slope of that line. Okay, geniuses. That's the average velocity, according to our physics definitions. And the average velocity simply is the slope of that line. Okay? So, filling out a lot of this chart is actually pretty easy. I don't think we'll go through the whole chart every time. But just make sure you could do it. So my change in position from 1 second to 2 seconds, okay, final was 30 meters and initial was 10, so plus 20 would be fine right there. From 1 second to 4 seconds, oh, does that still work? If I go from 1 to 4, I went plus 20. My average velocity, sorry, I meant to make this average. My average velocity from 1 to 2 is how much? What's the slope of that line? If I got single seconds, integer seconds on the bottom, and going up by tens, and I go up 2 and over 1, that should be plus 20 meters per second. From 1 to 4, I accomplish the same thing, but it takes 3 seconds. I should have made that a better even number. So it's like 0.67, 6.67 meters per second. Average velocity. Yeah, you can just average them. Does it really matter that we bent the line in the middle? Nope. Final position minus initial position divided by the total time that took. That's your average velocity. Okay. Is there a change in position, a displacement, at t equals 1.5 seconds? Are you sure? From where? Okay. You could do, you have to be careful. You would have to specify, if I say from 0, right? Then I'm okay. But I can't just say, what's the displacement at that instant in time? Displacement from where? Okay, you're safe to assume 0, I guess. You got to say from displacement from 0, right? If I give a span of time, there's a displacement over that course of time. But if I just have one little pinpoint in time, one instant, I don't necessarily displace during that instant. In fact, I definitely don't, if it's the smallest segment of time I can measure. Okay, so I would have to say displacement from 0. Okay, we can read the chart. We can read the chart to get positions. That's fine. From, oh no, from 1 to 2 seconds. Does it have a position that you can read? No, it's changing. No, I mean it has one, but that question doesn't have one answer. Okay, watch out. You can't, just because I can list all these things doesn't mean you can get them all from this graph. That's the point I'm trying to make. So it's like, no, I can't tell you that. Like a delta with a slash, whatever you want to say. Yeah, it's changing. I should put a no way sign. Ah, that's the eraser. Come on. Yeah, or NA. Whatever symbol you like. You can't tell me one position that represents the, unless it's stopped, right? You can't tell me one position for that span of time. It's constantly changing. I need some other variable to tell me the position. It's not on this graph. Okay, at 1.5, okay, it does have that same, now it does have a position. 20, at 3, it's at 30. At 5, it's on the way back down. Okay, it's back to 20. Cool. Can I measure the change in velocity from this graph? If velocity was the slope in the line, can I tell how much it's changing? From position? How much? Landon's insisting that I can? I can? How? Well, but you don't know how. Okay. Watch out. Okay, it's buried in there. I don't think I have enough information in there because I can see where it changes. Okay, the slope of the line is changing right here at this point. But that's like a calculus problem. What exactly is it at that slope? It kind of changes. It tilts from there to there. And then, oh, we've got a really interesting case over there. Here I can tell that it's continuously changing, but it might be really difficult to estimate what that slope really is. So again, this whole row, we have NAs, or non-existence. I can't tell you the change in velocity from this graph. I could maybe estimate it on that curve part. Okay, so you can't use every graph to answer every question. Okay. What about the acceleration, right? I don't know much about it. I don't know how much to measure it. What would accelerating look like on this position graph? Sure, right. Yeah, that's the curvy part, where I have consistent and steady change in my position line. I have a curved line, kind of like a parabola. All I can really say is I have a greater than 0, and actually on these straight patches, I can say a equals 0. I have a constant slope in my line. If this was x and y graph from Algebra 1 class, there would be delta y. Position is my y-axis, and time is my x-axis. So change in y over change in x, that is the slope. I should have written that. Just to make you write it one time. Okay. Your average velocity, or your instantaneous velocity, is the slope of this line. Okay. When it's a straight line, the slope isn't changing, and so my acceleration is actually 0. Anytime I can see, okay, between 1 and 2, acceleration is 0. From 1 to 4, ooh, nothing. Undefined. Or I should put NA. That's better. Because the acceleration is 0, and then it somehow does change, but we're not sure because you can't analyze that point. And then at 1.5, yeah, okay, acceleration equals 0. At 3, 0, 5, 0. Here it's something positive, but I can't really, without more information, you can't tell what the acceleration is. It just, you have some. And it's obviously sloping up and up more. Okay, any questions? You should have had a bunch of experience with this in Algebra 1, Geometry, earlier math classes. Can you kind of nod at me or give me thumbs up? You know about graphs and the slopes of lines? Okay. It might take a little bit, a week or so, to get used to judging these things in terms of physics. Okay. Same exercise. Here's a different, so example 2, there's a different situation, has a different velocity graph. But now I plotted velocity with respect to time. Now what things can we get off of there? You might be surprised. Okay? Let's not worry too much about judging them, like evaluating. If you can spot the numbers real fast, that's good. Okay? Like my velocity, between 1 and 2, to get the average velocity, I could just average 1 and 2. So it would be like plus 15. Cool. And to 1 to 4, I think it would still be plus 15. Yeah, it would. Oh, wait. 1 to 2. Oh, no, I divided by too many seconds. It's only 1 second. It's plus 10. Oh, no, no. No, I would average 20 and 10. Add and divide by 2, that's 15. Average velocity between 1 and 4, it's 10 plus 40, 50. Divided by 3, 16.7. I can just average them. Okay? Right at that time, 1.5, does it have an average velocity? These guys are now instant. If I give one timestamp, there's no average velocity. I could write the instant v instead. That's why there's instantaneous. You just read the number off the graph. I should have put instant and average on there to contrast, shouldn't I? Sorry. Okay. Can I get the change in velocity? Sure, from 1 to 2, right? So if there's no change in velocity for no time, there's no span of time, right? Delta t equals 0. But if I do give the time span, from 1 to 2, I increase 10 meters per second. From 1 to 4, I increase 30. Yeah, 10 to 30, 40. If I average 40 plus 10 over 2 is 25. Oh, math. I just divide by 2 things. 40, my final velocity, plus 10 is 50, is 25. I knew I thought through these numbers. Okay. How about acceleration? Is an acceleration the change in speed over change in time? Change in velocity, excuse me. So what's the acceleration on this graph? Yes, sir. Yep. It's the slope again. So that's actually really easy. Between 1 and 2, it has a constant slope. It's up 1 over 1, isn't it? So it's plus 10. Between 1 and 4, it's still plus 10. It's the slope. At 1.5 seconds, it's plus 10. It has a slope. Oh, that's even better. At 3, it still has plus 10. At 5 seconds, it's a horizontal line at 5 seconds. What's my acceleration there? What's the slope of a line that's horizontal? Yeah, okay, we need this Algebra 1 refresher. It's 0. And honestly, those are your only 2 options. I have some constant value, I'll probably be nice and make it an integer for acceleration, or I have 0 acceleration. We would need calculus if it wasn't that. Can I get displacement or position off of this graph? It's a velocity graph. Oh no. Okay, hopefully I didn't wait too long before springing on you the big trick. Okay. Oh. What was displacement again? The simplest equation? Isn't it? It's the average velocity times the time, isn't it? From 1 to 2 seconds, is there something on this graph that's equal to the average velocity times the time? If I look at this section, 1 to 2, trying to answer my first box. Right? Is it 15? The average of 10 and 20 is 15 times 1 second is 15. Okay, it sounds to me like you calculated it and didn't look at the graph, but you believe that it's okay. What picture is on the graph? That's 15. If I actually draw these boxes, every box is 10. If I have a foot by a foot, that makes 1 square foot, right? It's a foot on a side. Why can't it be 10 meters per second on one side and 1 second on the other side to make a box that's 10 meters? Why not? You can multiply meters per second times meters. That's what we're doing in this formula right there. If you multiply speed times time in your formula, you are actually counting area on the graph. The area under the line, so between the line and the axis, under the curve, we might say, if we were in a calculus class. But so here, the 15, here's a box that's 10, and another half a box, that's 5. Okay, from 1 to 4 seconds, okay, 1, 2, 3, 4, 5, plus 3 halves. Oh my goodness, 53 halves, 57.5? No, wait, half, each one half is 5, so 65. 75, I believe you. Okay. So wait a minute. If my span of time is 1 to 4, delta t equals 3 seconds. And I start, in that time span, I start at 10. And then I accelerate at plus 10. It's 75. What formula have we had that gives 75? V0 is 10. If I multiply that times the time, there's my 3 bottom boxes. 1 half a t squared. Okay, here's a t across the bottom again. This, the height of this is a times t, because that's the span times the slope of the line. That's how much up I went, and it's a triangle. So 1 half base times height is the area inside that space. So not only is like the average real, like this isn't just, oh, I have a graph and you also have to learn graphs. No, the graph is just another way to draw the logic of these problems in addition to equations. You could solve every physics problem graphically if you really wanted to, like by drawing shapes and pictures. That's what the ancient Greeks tried to do it when they were doing geometry. That's really what they were doing. They were solving physical problems by drawing shapes instead of writing down numbers and equations, because they were terrible at algebra. They didn't have that skill. Algebra, that was invented in Arabia. That's a different culture that invented that, and ancient Greece didn't even know about that until 1,000 years later. Okay, but you can do it either way. It's important to have some skill in both. Most people end up preferring the equations, but I think that's just because you've had more practice with that. Okay, because there's no delta, maybe that's better. You can't tell me displacement at these times. Although I guess you could add, maybe from 0, I have the same problem. Okay, can you tell me the position based on this graph? Yeah.
Would it be just from 0 to that point of the area?
Oh, again, we have this issue. You have to assume we start at 0, and okay, from these time points, I guess you could assume that we started from 0, but on this velocity, we clearly didn't start with 0 velocity. So that's a big assumption, and that's really too much for me. I'm not so sure we can start, we know where x0 is. It's definitely not on this graph. Nowhere on here does it tell you that I started at 0. Okay? So just know. You can't tell me the position. You can tell me the displacement if I give an appropriate span of time. And if you were clever, if you argued that on a test, if I worded the test question that poorly and you argued, okay, the time span should be 0 to 1.5 or 0 to 3 or 0 to 5, I'd have to agree with you. I'd have to specifically say, I want the instant. Can you tell me the displacement the instant that it's there? And if I was really careful, you'd have to say no, because I never told you where I started. Therefore, I don't know where I'm at. I know how far I've gone, the displacement. I do know that. And if you give me a time span that you can calculate using area under the curve or the total areas or the equations, you can tell me what the displacement is. But if I don't tell you where I started, then you can't tell me where I've gone, where I ended up.
You could do it as an expression of x0 plus a value.
You sure could. But if I didn't give you x0 on a test, then you couldn't get a numerical answer, is my point. Okay, so there's not enough information on this graph. It's okay, that scares some people. Sometimes in physics, in a particular representation, there's not enough information. Can I go on? Okay. I'm recording all of this. You want me to post this later? Okay. Acceleration. Right. So acceleration, I have no choice. It could be constant or it can be 0. Can you tell me change in position off of this graph? Displacement? Yeah, good. You're on to me now. No. Okay. There's no way. Because I don't know what happens in between. I don't know my starting velocity. Okay, there's no velocity. There's sort of a velocity on here. But can I tell you instantaneous velocity or even average velocity? No, there's no average, or should I say nor, or instant. There's no average, no instant velocity on this graph, and there's certainly no position. Oh, green. But hey, I could certainly read the acceleration values. Let's just put a check mark. Okay, there'll be a bunch of 30s and then zeros. Yeah, you can certainly read the graph, tell me what the acceleration is. What about the displacement, or I mean change in velocity? If delta v over delta t equals a, that's like the change in velocity equals a times delta t. That's our same area again. Okay, so you actually could, between 1 and 2, I could say I must have gained 30 meters per second of velocity because there's a box there that's an area of 30 in meters per second squared in seconds. Okay, from 1 to 4, that box has 30 and it's 3 across, so that's plus 90. At 1.5, that doesn't make any sense. That's one line. How much area do I have if I draw one line? You're smart to argue with me that it could be from 0, but that's not what I meant. Okay, from 0, and for any of these, 0, 0. So you can get the change. Notice how I'm kind of stepping up in time. I have meters. Meters per second is a rate, and then meters per second is the rate of that. I can go back one step using the area under the curve. So if I have acceleration, I can go back and get change in velocity. If I have velocity, I can go back and get the change in position. Okay? And everything else I can read off the graph. And if I don't have that, if I don't have slope, if I don't have area under the graph, then I don't have any more information. I can read the graph itself, and that's it. Okay? So when you read physics graphs, there's just three things. Okay, we're reading slopes. You can say slopes, which is like delta x over delta t equals v. You can get areas, which is delta x equals average velocity times time. I should probably make that average also. And you can just read the graph. You can read the points themselves. There's three things we can do. Okay. So it's actually fairly limited. We can't, it's not, I'm not making stuff up. We derived it today. I'm pretty sure, because I'm never 100% sure, I'm pretty sure there's nothing else you can squeeze out of those graphs. Okay, and we're halfway through. Perfect. I hope my video is short enough to record.